upload probably tomorrow, so.
Clear that.
Yeah.
Great.
Okay. So with that, our speaker tonight is Professor Neil Cornish, who was a College of Letters and Science Distinguished Professor in the Department of Physics at MSU. But I don't mean MSU as in our friends up in East Lansing. I'm talking about Montana State University. Since joining the Department of Physics at MSU in 1999, Neil has contributed to some of the century's most important gravitational and astrophysical discoveries. His achievements have helped position MSU among the top institutions in astrophysics and gravitational wave science. As you may recall, in 2015, scientists first observed gravitational waves. Dr. Cornish's LIGO group reconstructed the gravitational wave signal from the collision of two black holes in a galaxy 1.2 billion light years from Earth. At Montana State, Neil directs the Extreme Gravitational Institute and has maintained an active research group of 3 or more doctoral students. 11 students he mentored at MSU have received their doctoral degrees. In the classroom, Neil shines as an undergraduate instructor, consistently receiving high marks from students. Professor Cornish has published well over 320 scientific papers, and that's a dated number, in leading international journals, has served on numerous committees advising NASA on general matters, including its planned laser interferometer space antenna mission. He is on the scientific advisory board of the Max Planck Institute and has given numerous invited presentations at universities and international meetings. And speaking of presentations, we're honored to have Neil with us here tonight to talk about his work. So with that, let's please give him a warm welcome.
Well, thank you all for inviting me. Yeah, and the reconstruction of this first gravitational wave event is actually up on my title slide here. The reconstructions you see down below are the ones produced by my group actually on the day that detection came in, and they're the signals in the two LIGO detectors, the one in Hanford, Washington, and the one in Livingston, Louisiana. And you know, that day when we first saw this, this technique that we use actually just pulls the signals out from the data with no assumptions that it has anything to do with Einstein's theory or anything I'm going to tell you about, but just like purely just pulling the signal out from the noise. And we looked at those, and they looked just like the predicted signals for what a black hole merger looks like when you use Einstein's theory of gravity. So we were very excited that day. We were very confident that we'd actually got our first detection, unless someone had been trying to trick us and put a simulated signal into the data just to see if our analysis was working. But turns out the mechanism to put simulated signals in wasn't even functioning at the time. So once we found that out, we knew we had something. So anyway, that's the story I'm going to be telling, is a little bit about the dawn of gravitational wave astronomy and where we go from there, where, what's coming up. So I'm going to start with just a little bit of an overview of Einstein's theory of gravity and black holes, just putting all this into context, talking about then getting into gravitational wave astronomy and what that means, and then talking about that first detection and what's happened since, and the excitement that's still growing, I think, around this new branch of astronomy. So, as I'm sure you know, I'm never quite sure with my audience at any particular event what their background is, but as I'm sure all of you remember from school, Newton's theory of gravity tells you that the force between two masses falls off inversely as the distance squared between them. And using that description, was able to explain, say, the Keplerian orbits of planets And then Einstein came along and said, no, there's actually no force of gravity. What's actually happening is when you have a massive object like this big apple here, the energy and of this apple actually distorts space and time, and then objects move around in that distorted space-time. So there's no forces per se, but just objects moving around in a space that's no longer flat. So it's really a radically different description of gravity. Now, at the energy scales on which we live, we know of 4 fundamental forces. We've got gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. Both the weak and the strong nuclear forces are short-ranged. If we scale anything against everything against the strong nuclear force inside an atom, inside a nucleus, and then work out the relative strengths, well, the weak nuclear force, as its name suggests, is 13 orders of magnitude smaller. Electromagnetism is 2 orders of magnitude smaller, but then when you look at gravity, and it's 38 orders of magnitude weaker than the strong nuclear force. So if you're trying to describe the structure of nuclei, you don't have to worry about gravity. Some of the differences, though, are gravity, just like light, so electromagnetism is long-ranged, it has an infinite range, and one of the key differences is that gravity just comes with one sign, so it's purely attractive. So while it's a weak force, it just builds up and builds up and builds up. So actually, on the largest scales of the universe, gravity dominates not just the structure of the universe, it is the most important force in terms of the energetics of the universe. It's the major energy source that actually shapes galaxies and through black holes, which is paradoxical enough, right? Because we always think of black holes as objects that don't allow any light to escape, but paradoxically, black holes are the brightest objects electromagnetically in the universe as well from their surrounding matter. But in talking about energy, I like to sort of establish an energy scale, and in physics we have many different units that are used for energy, but I'm going to introduce a somewhat different unit of energy that I'm going to use tonight. It's based off the most powerful energetic event that mankind has ever generated, which is the test that the Russians did. This is the largest thermonuclear explosion ever, and during that explosion, several kilograms of matter were converted into energy. So, Einstein's E equals mc squared, we had several kilograms of matter. And so for that, I introduced the unit of energy of 1 kitten. And so it was the energy equivalent of taking a kitten and vaporizing it. Okay, so that was 1 kitten. That's basically the most powerful event that humans have ever generated. Comparing that on the scale of astronomical objects like the sun. So the sun, vast thermonuclear furnace, and the sun is actually consuming vast numbers of kittens. In fact, it is 1 billion kittens per second is the equivalent burn rate of the sun, okay, in terms of just E equals mc squared release of energy. So the sun is, a powerful source, but these really pale in comparison to the energy output that we're going to look at for objects that are gravitationally powered. So when we have, for example, this is an animation from a simulation of 2 black holes, and we've got the little black holes there, and what the blue and yellow is showing you is the curvature of space-time. And I'll talk more about this in a moment, but anyway, moving in and merging in a black hole merger, the energy release rate, and this actually is independent of the mass of the black hole, the energy release rate is 1 billion trillion kittens per second. So vastly more powerful than the output of a sun. And in fact, when these gravitational wave events occur, they're releasing more energy than the combined output of every star and every galaxy in the universe, right, in a single event, no matter how big the black hole is. All that changes, the bigger black holes, they have the same luminosity. They just they emit for longer. So the total energy emitted by a large black hole is greater, but the actual peak luminosity is independent of the mass of the black hole. So they're always as same brightness in gravitational waves. And this, yeah, so getting back to Einstein's theory, this is actually the way that John Wheeler described Einstein's theory, was that matter tells space how to curve, and then space tells matter how to move. So we've got massive objects, any kind of concentration of energy in the universe, warp space-time, and then objects have to follow the straightest path they can in that warp space-time. So that's the idea in Einstein's theory. And when you apply this to a collapsed star, you end up with a picture like this. And what we have here is, this is a spatial slice of a black hole. And these little cones that you're looking at, you've got the red cone and the green cone. I hope everyone's able to see, isn't red, green colorblind, but the red cones are these are all the areas into the future that you could communicate to. So that's known as the future line cone. And the red is the past of each of these points. And you can see what actually happens in a black hole is that it isn't that gravity is, sucking things in. It's actually space-time is warping. So as you go into the black hole, the green, the part of the cone that points towards your future ends up pointing towards the center of the black hole. So the reason you can't escape from a black hole is not because of a gravitational force, it's because the center of a black hole, once you pass through the event horizon, actually lies in your future. So it actually becomes your future. You cannot escape your future. So you are driven to encounter the singularity because it actually becomes a point in your future. So it's that extreme warping of space and time actually turns what we think of as a place in space, the black hole singularity actually becomes a point in your future. The black holes have actually been mathematically described for a long time. So for a non-rotating black hole, it was first described back in 1918 by this paper by Carl Schwarzschild. And so at the time, no one really quite understood what to make of this solution. If you plugged in numbers for something like the Earth, for example, you found that this strange region where light would become trapped actually occurs at a radius of a couple of centimeters for an object the mass of the Earth. So it just wasn't really considered to be all that relevant because the Earth is thousands of kilometers in radius. So this solution was for empty space, and the Earth is an empty space. So it was just considered to be like a mathematical curiosity. And really the full sort of physical nature of these black hole solutions wasn't really understood until the work of people like Carter, Penrose, and Hawking in the 1960s and 70s, that we actually really understood physically what these solutions described. And for a long time, though, I thought maybe they're just curiosities that come out of the formal equations of Einstein, but perhaps they have no relevance, in nature. But we now have this picture that in the life cycle of stars, as they, if they evolve, if they're more massive than our sun and go through a red supergiant phase and then explode in a supernova, or maybe just collapse directly if they're even more massive. They can actually, the end result of a supernova might be either a neutron star, so an object, you know, maybe about 1.5 times the mass of the sun that's crushed into a radius of about 12 kilometers, 10 to 12 kilometers, or it might even get crushed further all the way down to a black hole, or you could even just directly collapse. So we see black holes as being sort of possibly stellar remnants, so the end result of failed stars that have collapsed, and then more massive black holes could form through other mechanisms. So this was the sort of the possible theoretical picture of how we might form black holes, but it wasn't until really the 60s we started getting any kind of observational evidence. And so the two of the main extreme stellar remnants. So for a neutron star with, like I mentioned, about 1.5 times the mass of the sun and a radius of around 10 kilometers or so, if instead it was a black hole, it would have a radius of about, let's see, it's around 4 kilometers or so. So a neutron star is awful close to being a black hole in terms of how compact it is. So if you were to like scoop up a teaspoonful of matter from the center of a neutron star, it would have the same mass as 1 billion African elephants, right? So just 1 teaspoon of matter so it's incredibly dense. It's actually denser than the matter at the center of a nucleus of an atom. The electrons have been forced, overcoming, they've been forced inside the protons and become neutrons. So these are some of the objects, black holes and neutron stars are some of the objects that are some of the key targets for us to try and explore using gravitational wave astronomy. We want to understand the properties of the material inside a neutron star, which are at densities that we can't reach on any kind of earthbound accelerators. So we're hoping to be able to use gravitational wave observations of the collisions of neutron stars and black holes as a way to really probe the properties of matter at these extreme densities, and also wanting to understand how gravity behaves in the extreme regions of a black hole. So as I mentioned, these properties of understanding black holes and how they relate to collapsing matter was described, and the ubiquity, the fact that black holes really must exist if Einstein's theory is correct, was first proved in 1965 by Roger Penrose, who proved the first of the so-called singularity theorems that actually said under very general conditions black holes would form in Einstein's theory. So he actually said, you know, not only are these exotic objects, these exotic solutions to Einstein's theory possible, they really must occur in gravitational collapse. So that was back in 1965. And then around the same time, we had the first observations in X-ray of Cygnus X1 in 1964, which we now interpret to be a so-called low mass X-ray binary, where we've got a black hole that is pulling matter off a orbiting star that then goes into a very energetic accretion disk, where that matter swirling around the black hole, as it plunges in, its gravitational energy partly gets dissipated through viscous and frictional type forces into heat and light, all the way up into X-ray and harder wavelengths. And so we actually have now somewhat indirectly detected a large number of black holes in these X-ray binaries, where we think that the X-ray, we've got these big jets and everything, are powered by the gravitational field of the black hole. So it was the beginning observational evidence for black holes back in the mid 60s, and also the theoretical proof that they were somewhat inevitable in Einstein's theory of gravity. On larger scales, we see often associated with galaxies, these enormous jets of material jetting out, and that is, we believe these are quasars or active galactic nuclei, where we've got a galaxy that has a large central black hole. As material falls into the black hole, it gets some of it gets accelerated and jetted out. The way that we say it is, black holes are messy eaters. It's actually very difficult to get matter to go into a black hole. It's got to burn off its rotational motion to get into the black hole. And so black holes actually spit out and accelerate these huge jets of material. And that actually controls the structure of galaxies. So galaxies, the structure of a galaxy is intimately connected to the central black hole. And it seems that pretty much every large galaxy hosts a very massive black hole at its center. We see these all the way back to the very early times in the universe. And one of the sort of things that's really come up over the last decade or so in astronomy is realizing that black holes are actually the key to understanding the properties of galaxies and clusters of galaxies, that they're actually driven by the energetic emission from the central black holes. So black holes and gravity actually are the, not through their gravity. I mean, people, when you tell people, you might have heard of these relationships between the, say, the mass of the central black hole and then the mass of the contained in the stellar bulge at the center of each galaxy. There's these very tight correlations, and people go, well, that's obvious, right? I mean, black holes, they suck everything in, so it must be the gravitational pull of the black hole that's holding in those stars. Well, that's not it at all. The black holes only affect the stars that are very close into the center. They are not the gravitational field of the black hole. The mass of the black hole is a tiny fraction of the mass of the bulge. And so it's actually the gravitational effect of the other stars and also dark matter that actually shapes the galaxy. The black hole is essentially irrelevant in terms of its gravitational pull. It is relevant, though, sort of ironically enough, from its huge emission of energy from the material that it accelerates and spits out. So black holes are, some of the brightest objects in the universe, electromagnetically as well as in gravitational waves. If we look at the center of our own Milky Way galaxy, in Sagittarius, and we have there's a intermittent X-ray source, Sagittarius A star, and then if you look at those stars that are surrounding Sagittarius A star and track them carefully over time using infrared observations to see through the dust, and do this for many years, you actually see that they're moving around and they're orbiting a point at the center of the galaxy, but we don't see anything really there. It happens that that point corresponds to where some of the X-ray emission's coming from. And these observations, we can use them and by using the orbital dynamics to actually infer that there's a black hole there with a mass about 4 million times that of our sun. And so we have observations there, since we don't really see any other emission from this object, that we have a black hole at the center of our galaxy. And as you all know, the combination of these discoveries, first of all, Penrose for predicting that black holes really were something we had to take seriously in Einstein's theory, and then Gens and Gers for leading the groups that did the observations of the galactic center to see that we have produced very strong evidence that we have a black hole at the center of our galaxy. They were awarded the Nobel Prize in 2020 for that discovery, those discoveries. In the case of Roger Penrose, he had to wait considerably longer to get his discovery rewarded. But So moving on to gravitational wave astronomy, let's go back all the way to the dawn of electromagnetic astronomy with Galileo. And of course, people had been observing the heavens just with naked eye astronomy prior to Galileo, but then when he heard about this new invention of a telescope and built his own telescopes and started using them to do observations, that's where modern astronomy really began. And of course, discoveries like the moons of Jupiter and then the phases of Venus and really radically overthrowing the idea that the Earth was the center of the universe was the beginning of astronomy back over 400 years ago now. And following that, we had a steady increase in the capabilities of the telescopes, and driven by rocketry and the development of radio technologies, a lot of that during the Second World War. We then had the expansion to be able to put telescopes up above the Earth's atmosphere, and also radio telescopes here on Earth, so we could then observe objects across the entire electromagnetic spectrum, all the way from gamma rays and X-rays all the way down into radio. So a single object like the in this case the Crab supernova remnant, by being able to view it across this this wider range of the electromagnetic spectrum, it gives us far more information about these objects. And so that was really the story of last century, was the development of and then a composite like this of being able to have a much better understanding of objects like these supernova remnants by doing these multispectral observations. So that was really what was the transformation in the last century. This century, the two big developments that we're heading to are time domain astronomy, where we're going to have we're already getting in there with the robotic telescopes that are able to go back and image large fractions of the sky every few nights, so we can start seeing a lot more transients. And then of course we also have the gravitational wave astronomy as the other big new development for this century. So yeah, back in our fundamental forces with gravity, as I was mentioning, the idea that gravity is this warping of space-time, so that, for example, if you had something like a big object like, say, the sun, causing a warping of space-time, then you'll have a smaller mass like the Earth, then sort of essentially orbits around following a straightest path as it can in that curved geometry, so it orbits around. And you notice that even the Earth, as shown in this depiction here, creates a dimple in space-time, a somewhat smaller one, so that when you then have two objects moving around, they each create a little dimple in space-time that as they orbit each other, they, like putting your finger in a pond and swirling it around, they produce ripples. Those ripples are carrying off energy and angular momentum, which causes the orbit to decay. And it's those ripples which carry off energy from the system that we seek to detect with gravitational wave detectors. So if you're interested in making gravitational waves at home, I've got a little recipe card here on how you can do that. And the ingredients, you just need a large amount of mass and energy. It doesn't matter what type, any kind of mass or energy. The directions, you just squish it into a small lumpy blob. It's even better if you make two blobs, and then you sort of shake or stir vigorously. So that's how you make gravitational waves. As I wave my hand around, I'm making gravitational waves, but not at a level that we really have any hope of detecting. Einstein first predicted gravitational waves in this paper back in 1916, and he put in some numbers for various astrophysical objects and concluded that these waves would be so incredibly tiny in terms of their effects that it was essentially hopeless to ever hope to observe them. So he thought they were a theoretical curiosity that there was really no way that we would ever be able to build any kind of device that could detect them. So that was the status for many years. The way that a gravitational wave works, it's a bit like you've all heard of the expansion of the universe. Well, a gravitational wave is actually an oscillatory stretching and squeezing of space-time. So if we had a gravitational wave coming out of the screen, then in the direction transverse, you actually get this squeezing in and out. So Einstein here, this was what would be happening to Einstein's head if he was unfortunate enough to be nearby to a merging pair of black holes with the gravitational waves stretching his head back and forth. So that leads to the basic principle for how we might detect these waves, and that effort started all the way back in the 50s. But the stretching is really minute, so that when you put in the numbers for, say, a black hole, a pair of black holes running into each other with masses maybe tens of times that of the sun, the amount of stretching is minute. The Earth's orbit around the sun, for example, would be stretched by about the width of an atom. So you're looking for a very, very tiny effect, okay? That's the challenge. That's why Einstein thought this was hopeless. But not everyone thought it was hopeless. Joe Weber set out, University of Maryland, to build what's known as an acoustic bar detector. So this big cylinder of aluminum with various kinds of transponders on it. And his idea was that if this Weber bar was like a big tuning fork. It has various resonant frequencies, and if a gravitational wave came in at that frequency, that stretching by a resonant excitation, just like if you resonantly excite a wine glass, then you can drive large oscillations and maybe pick this effect up, right? So Weber and looked for gravitational waves using this device. He actually claimed a detection, but there was errors in the analysis that were done. Other people built more sensitive versions of that kind of detector, but were unsuccessful in making any kind of detection. But in the 70s, some other researchers started thinking about, okay, how might we try and detect gravitational waves? So instead of Einstein's head here, what I've got is a ring of masses, those red dots with a circle sort of showing you, and they're getting stretched. And if you then look on the bottom of the screen where I'm sort of showing it as in time, it's alternating stretching in each direction. And imagine if you were to measure the distance between three of those masses, you would see that the distance between those masses alternately gets longer in one direction and shorter in the other, and then it goes back to being longer in the other direction and shorter in say the vertical direction there. So if we could track the distance between these masses very accurately, we might be able to measure this stretching directly. And so the idea is to use lasers. So if you take a laser and you throw it through a beam splitter, bounce it off an end mirror, if it comes back with the wave, the laser light meeting crest to crest and trough to trough, then you get constructive interference. If it comes back, if it's out of phase by a half wavelength, then it comes back crest to trough and trough to crest, and it cancels out. So the idea is you actually build a big interferometer, as this is called, and you sit very close to one of these destructive interference fringes, so most of the light isn't leaking out. And then if something comes along to disturb the system, it goes from being dark to allowing, say, one photon through. And so we can detect a single photon coming through, and we've got huge numbers of photons in this beam. So even the tiniest little shift doesn't have to even be anything like a full wavelength, just a tiny fraction. We can actually measure shifts in the wavelength instead of a wavelength on 2 to go from destructive to constructive interference, even a shift of parts of 10 to the minus 14. So 14 orders of magnitude smaller shift we can actually detect. So this is the principle on which our detectors work. And so we have currently actually 4 detectors. I only picture 3 of them here. We have on the top left, we have the LIGO detector in Hanford, Washington. On the bottom left, we've got the LIGO detector in Livingston, Louisiana. And then in the middle here, we have the Virgo detector just outside of Pisa in Italy. We now have another detector in Japan. And these detectors are all typically kilometer-long arms, and they're capable of detecting a change in the relative length of the light going up and down one arm to the other that is 1/10,000th the width of a proton. So incredibly sensitive devices. That's equivalent to being able to measure the distance to Proxima Centauri to the width of a human hair. So that's the measurement accuracy that we have with our gravitational wave telescopes. So yeah, Einstein didn't think it could be done. Ironically enough, it's actually lasers, which are based on a principle in quantum mechanics that Einstein helped discover, the Bose-Einstein condensates, which actually are behind the mechanism for coherent light in a laser, is actually what makes this detection possible. There's an interesting analogy here. If you think about this, I mean, it seems crazy, right? How can we detect the movement of these mirrors? Because the mirrors are made of atoms, and certainly the surface of the mirror is not smooth on the atomic scale. We've got the variation, at least on an atomic scale of angstroms, which is many hundreds of thousands of times larger than the scale on which we're trying to measure the movement. But it's actually, our ear does something very, very similar. So the tympanic membrane in our ear, in our eardrum, that we use to sense sound, of course, is made of skin cells. And those skin cells, which I show on the right electron microscope picture, have a scale of around 300,000 angstroms. So with 1 angstrom being roughly the scale of an atom, right? So, and at the threshold of human hearing, at least for a young person, we can actually detect a deflection of our eardrum that's 1/10 of an angstrom. So the 1/10 the width of an atom is right at the threshold of hearing, how much your eardrum's actually moving back and forth. And that's despite the fact that our eardrum is made up of skin cells, which are many, many times, larger than that. So it's very similar to what we're doing with LIGO. We're actually really sensing the bulk displacement, the actual movement of the center of mass of those mirrors, even though the surface itself is quite rough. The laser beam is spread out across a large portion of that surface. So there's a lot of averaging that goes on that allows us to actually measure this minute effect, even though it seems ridiculous given that the detector's made of atoms. So that's the story of how the detection, how the instrument got built and the theory behind it. And then a long time ago in a galaxy far, far away, 1.2 billion light years away, we had the first signal that we picked up, the merger of 2 black holes, each around 30 times the mass of the sun, coming in 2015, in September 15th, 2015, sorry, 14th. And 1.2 billion years later, those gravitational waves passed through the Earth. They were obviously moving a lot faster than this animation, and this effect is greatly exaggerated, but shaking the Earth like a giant ball of jello. And that signature was picked up in the detectors. Here is the output of the detectors from that time, where we've done some some processing of the time series This is time running along here in seconds. And we've cleaned up the data here with some filtering. You can see a bit of a disturbance. And then using an algorithm my group developed, we're able to drop out the noise and just pull out the signal part. And there's the signals in each detector, which matches that of the predictions of Einstein's theory of what you would expect to see when two black holes collide. And that's what we showed in the first figure of the paper in Physical Review Letters, where we announced the detection of this black hole merger. And that middle panel there shows in red the prediction of Einstein's theory, solving Einstein's equations on a computer is the red trace, and then the shaded behind that is actually our reconstructed signal. So that's the work that, for example, my group did here. And so it was very exciting for us to actually have the work of my students and I showing up in the figure 1 of the paper that announced the first detection of gravitational waves. So that was a highlight for my career and that of many of my students who were involved. This event liberated the equivalent of 3 suns in a fraction less than 1/10 of a second. Those 3 suns getting turned into energy, which was 1 billion trillion kittens vaporized. So this event, outshining all the stars and all the galaxies in the universe at that moment, but in gravitational waves. And for this discovery, Ray Weiss, who came up with the basic design for the LIGO detector back in the 70s, Kip Thorne, who developed most of the theoretical framework for studying gravitational waves, and Barry Barish, who led the project and got it built. They were jointly awarded the Nobel Prize in 2017 for this discovery. Since then, we've detected almost 100 signals, and the detectors are about to come back online again. It's been delayed because of the pandemic. They will return to service much improved in March of next year. So there's been going through various upgrades, which took longer than we hoped because of all those delays. We couldn't have people on site for many months. And in addition to the merging black holes, so what this plot shows is the masses in units of the mass of the sun in blue black holes colliding together to form another black hole, or in orange 2 neutron stars colliding together to form maybe a black hole, or maybe temporarily a little neutron star. And we've actually had black holes and neutron stars merge to form a black hole. So we've now seen quite a zoo of events, roughly 100 total events now, involving some of these extreme remnants. August 17th, 2017 was a very exciting day. That's when we had, and I've got some sound playing here. That sound was the gravitational wave. That ding is just an illustration of what it might be at the Fermi gamma ray telescope, where a very high energy gamma ray hits one of the crystals that is used to detect the gamma rays. Gamma rays really behave more like particles than waves, because they're so energetic. That signal that I played for the gravitational wave was actually directly what you would have heard if once we clean up the data and drop out the noise. That's exactly the gravitational wave just turned into sound. So turn that vibration into the movement of your speaker, and that's what you hear. It's completely in the auditory band that these detectors work. And so this was the first detection of a merging pair of neutron stars. Roughly 1/3 of all the professional astronomers on Earth got involved in observing this event. They tracked it down to this particular galaxy, where first there was this blue blob that hadn't been seen before, rapidly faded to the red, and then sort of disappeared, at least from visible, showed up in all across the electromagnetic spectrum, still actually showing up in radio right now, and reflaring in X-ray. And during that collision, there was something called rapid or R process nuclear synthesis with a very neutron-rich material actually produced multiple planets worth of platinum and of Jupiter's worth of platinum and platinum and gold. In fact, we think that most of the gold and platinum and also things like iodine are actually produced in neutron star collisions. And then these neutron stars almost certainly collapse to form a single black hole. And so this material was all generated, all this gold and platinum was generated within a few thousand kilometers of a black hole. So if you actually happen to have any gold or platinum, maybe when you take it out and look at it next, if you maybe have a ring or something, look at it now, that you're actually holding on to something that formed in the close vicinity of a black hole and then made its way to, that material made its way to Earth. So it's probably part of the reason why it's so expensive, a rather long journey that it had to make from the environs of a black hole to the jewelry store near you. So when you look at the periodic table of the elements, all of the elements that are primarily colored light yellow, we believe from an understanding of the nuclear synthesis and the measurements of this event, they're actually primarily generated by merging neutron stars, and including iodine, which is key. If you didn't have iodine, it's key for a lot of metabolic processes. So we wouldn't be able to live without it. So not just nice jewelry, but also other elements that we rely on were generated from two collapsed stars that then collided with each other. So it's a very much a Rube Goldberg type event to generate such matter. Right now we have the detectors I told you about. There's a smaller one also in Germany called GEO. We're going to place a new detector in India that's in the process of happening right now, and we have this other detector which has joined us, which is underground in a mountain in Japan. So we currently have this network of detectors. Most of them will be back online next year, and we hope to make a lot of new discoveries with those. But we're not stopping with this generation of detectors. There are plans going forward now to actually expand gravitational wave astronomy, and we're going to have upgraded ground-based detectors, mostly underground. And on the right, this shows the neutron stars on the left and black holes on the right. The sort of dashed, the light blue dashed line is how far out in the universe we can see currently. So imagine the Earth is sort of at the center of this picture. This is sort of how far out we can see. And so far, we only see out far enough to be able to capture a very small fraction of all the black holes in the universe and a very small fraction of all the neutron star binaries in the universe. As we go out, the dark blue is coming soon. And then we go on to these future detectors, which will actually get us out so we can see out to measure every single black hole merger, stellar remnant merger of every object in the universe. So those are the next generation detectors, which hopefully will be built and operating next decade. But in between, we've got a series of upgrades. So the dark blue and the orange are upgrades of the existing facilities that are going to be ongoing in the next few years. So we're going to be dramatically expanding our reach, and we're going to go from having 100 events to having hundreds of thousands of events, which will allow us to do a lot more detailed studies, and also many of the events will be observed a lot more cleanly. So we'll be able to start really probing the structure of neutron stars, really testing Einstein's theory of gravity much more precisely than what we already have. Going beyond these ground-based instruments, which operate in the range of human hearing between, say, 10 hertz and a few thousand hertz, which is really the range of human hearing. Down below that, we are planning to launch some detectors into space. There's a project that's joint between the European Space Agency and NASA called LISA, the Laser Interferometer Space Antenna. I'm a member of the NASA science team for that project. And there's also a couple of Chinese projects to put detectors in space. And the reason we need to go to space is that on the Earth, we have earthquakes, and it's not the shaking of the earthquake, it's actually the squeezing of the earthquake. The earthquakes actually cause a density wave in the Earth, which changes the Earth's gravitational field. And there's no way we can shield against the shaking because we have very good seismic isolation, but we cannot shield against gravity. So it's actually the perturbations of the Earth's gravitational field due to an earthquake. The earthquake actually squeezes the matter in the Earth in and out, which creates a varying gravitational field that prevents us from being able to detect lower frequency gravitational waves from the Earth. So we have to go to space, and there would be looking for much more massive systems because the frequencies scale inversely with the mass. So if you want to detect very massive systems like the black hole at the center of our galaxy, we have to go to space. If you want to go to even more massive, we have a technique we're using now using pulsar timing, where we're looking for those massive, supermassive black holes at the center of galaxies. And so with pulsar timing, we're observing millisecond pulsars. So these are rapidly rotating neutron stars that have radio emission that flashes by the Earth. And these rapidly rotating ones, they're rotating hundreds of times per second. And they're extremely stable rotators. In fact, their rotation rate is more accurate than the basic atomic clocks we have on Earth. So by looking for small changes in the arrival of the pulses from these rapidly rotating neutron stars, we can actually use that as a galactic-sized gravitational wave detector. So we're using a collection of radio telescopes around the world. We have 3 different collaborations, one in Europe, one in Australia, and one in North America that I'm part of. Unfortunately, we lost Arecibo a few years ago, so we're now down to mostly the Green Bank Observatory plus the Very Large Array and a few others. But we've now got new detectors coming. We have the FAST detector in China. We have the CHIME detector in Canada, Meerkat in Australia and South Africa, and the Square Kilometre Array getting built. So we will have many, many more pulsars. I expect we'll probably have a detection of very low frequency gravitational waves using these techniques probably by next year, based on what we're seeing in the data right now. So stay tuned for that. We think we're on the cusp of detecting very, very low frequency gravitational waves from merging, well, not merging, but orbiting supermassive black holes that are 1 billion times more massive than the sun. And so we think that when galaxies merge, which they do throughout the history of the universe, their central black holes get together and start giving off gravitational waves. And we think that we're getting very close now. We've got hints of the signal showing up. We're just trying to sort everything out. It's a complicated measurement, but we're hoping that we can figure everything out and maybe be able to say that we've detected some waves from merging supermassive black holes very soon. And then a little further into the future are the space-based detectors, like the Laser Interferometer Space Antenna. This will be a constellation of spacecraft. Obviously, the Earth and the Sun aren't to scale here, nor are the size of the spacecraft themselves. They'll actually only be, a couple of meters across. However, what is almost correctly to scale is that the detector is going to be about twice the size of the sun. So its collecting area is about twice the size of the sun. This triangle of spacecraft will have lasers going between them to track the distance and creates a detector that is 2.5 million kilometers in side length. So bigger than the sun and able to detect signals from things like a small black hole falling into a black hole the size of the one at the center of our galaxy, which is what this animation is going to show. In Einstein's theory, the orbits of objects are not Keplerian. They do all sorts of crazy things. They don't stay in the same plane. They go all over the place. This animation is going to show you where this smaller black hole, you see you got a small black hole and a larger black hole here. The smaller black hole, they're orbiting around each other. And it's going to show you a trace, which is where that black hole spent the last day of its orbit. And along the bottom is going to be the gravitational waves that it's emitting, shown as a wave and also turned into sound. So there's a lot happening here. And these are the kinds of exciting events that we plan to detect or hope to detect with this future space-based detector. And then it got swallowed at the end. So this little black hole going around the big black hole is tracing out the space-time of this larger black hole. It's going to allow us to do absolutely incredibly precise tests of Einstein's theory of the structure of black holes and the material surrounding them. So this is really what this is probably one of the most exciting things that we hope to see with these future detectors. And I will leave you with the thought that, well, sorry, I forgot, there was one other thing. My personal interest at this point in gravitational waves is we found lots of things that we sort of expected to see. We expected to see black holes merging. We expected to see neutron stars merging and neutron stars and black holes getting together. But what about something completely wild that we've never seen before? So maybe something that's not predicted, or just a very exotic phenomena from the early universe. There could be things like cosmic strings, bubble nucleation from various processes that happen in the early universe, various kinds of phase transitions. There might be effects related to string theory. There might be completely unexpected, like that's what the question mark stands for here, completely unimagined astrophysical events that we might pick up in gravitational waves. So my hope is that we're going to detect some things that are completely exotic, that no one's ever thought of before. Here's some examples of some exotic things that people have thought of, but I'm actually probably even, those are exciting, but then the completely unthought of ones, the new discoveries of exotic phenomena that no one's considered, that's really what I think is going to be the most exciting thing in gravitational wave astronomy. And my final thought is, if you look back, Galileo's telescope had a 37 millimeter diameter lens. The European extremely large telescope that's getting built right now has a mirror that's 39 meters, right? So over 1 million times the collecting area. Obviously far greater angular resolution. So that's been the progress in the last 400 years in optical astronomy. You know, we're just starting out right now. We're back. Currently, our instruments are like Galileo's first telescopes. And where will we be, 10, 50, 100 years from now? Thank you.
Thank you, Neil. We have questions for Neil. Yes.
Just thinking about the incredible sensitivity of LIGO, what was it, like a part in 10 to the 21st for strain?
Right. Yep.
Were there any, one or two sort of major technological breakthroughs that allowed that to happen, or was it just, literally decades of small improvements?
No, there was several major breakthroughs that happened, plus a lot of, smaller things. One was so one of the people who was instrumental to getting the instrument working was Ron Drever, who the locking LIGO works by having actually cavities where the light is bouncing back and forth, and you're building up the power in those cavities until you have like megawatts of circulating power. And Ron Drever was one of the people that was key to developing this, being able to lock these cavities and get that huge accumulation of power. There was also engineering kind of developments, the coatings on the mirrors. You need very special coatings on the mirrors. You need to be able to develop very special kinds of seismic isolation. You need to develop very large, very powerful laser systems. So some of them were sort of more incremental, but there were some major, unfortunately, Ron Drever, he was still alive when we made the first detection, and he was aware of it, but he passed away before the Nobel Committee got around to handing out prizes. So he would have arguably been in consideration for being named in that prize. Yeah, there were many contributions like that, but yeah, the laser technology, and now where they're going with the laser technology is really incredible. Our sensitivity is now limited. We're getting to the point where we're limited at both high frequencies and low frequencies by quantum mechanics. At high frequencies, it's the discrete nature of light, that it's actually individual photons. At low frequencies, it's actually the radiation pressure of the photons striking the mirrors, right? So the light itself striking the mirrors perturbs them, and so they're shaking, the photons themselves shake the mirrors, and so we're up against Heisenberg's uncertainty principle. And so we actually are using things like quantum squeeze states now, and so both the LIGO detectors and the detector in Italy, the Virgo detector, both use a macroscopic quantum states where we use quantum squeezing to actually improve the sensitivity. So these are, yeah, so we're not done yet with the incredible technological advances which are increasing the sensitivity. We're basically now beating the quantum limit by using squeezing.
Yes, Dimitri.
I had a quick question. One of your slides, you were showing the predicted increased ranges in future observatories. I don't know if I read that right, and I haven't studied too much on astrophysics, but a redshift value Z of what seems to be 80 there, how close is that getting to the Big Bang? Do you know off the top of your head?
Yeah, so, well, a long way from the Big Bang, but just to give you a scaling, I actually always, there's a handy online calculator that Ned Wright, it's called Ned Wright's cosmology calculator, and you can like plug in a redshift and it'll give you a luminosity distance or whatever, right? Because I actually have a hard time getting these numbers straight myself. When it close in, there's a linear proportionality between redshift and distance, which is the Hubble law, right? So you just put in Hubble's constant and off you go. But just to give you a sense here, the cosmic microwave background radiation, which is the furthest back we can see in electromagnetic radiation, is at a redshift of 1100, right? So that's where the cosmic microwave background radiation is coming in. If you've seen the recent results from the Webb Space Telescope, I think the record holder, even though they keep on beating it week after week, I think there was something at like redshift 12 or so for the most distant galaxy that they've imaged with Webb now. I think that they might have beaten that already. I think there might have been a new one this week. But anyway, sort of that order, somewhere between Webb's going to be observing galaxies out as far as maybe redshift 20. We don't really think there are any galaxies much before that because they had to form up. So
I did read a study. It's still controversial on whether it's dust or not, but they were saying redshift 20.6.
Yeah, so it gets tricky, right? Because are you mistaking a more distant galaxy for actually something that's suffering through various dust extinction and things like that? So that isn't my area of expertise. The great thing about gravitational waves is they don't care about dust. Gravitational waves go through everything. They go right through a neutron star. There's no material, you know, in the universe that can stop them. So we don't have to worry about dust. They're hard to detect, but the flip side of that is that they're hard to stop. So yeah, they come right through everything. We can actually observe all the way back to the Big Bang, all the way back, way past redshift 1100, because we're not stopped by the charged plasma in the early universe, right? So gravitational waves offer us the ability to measure processes that happen in the first fraction of a second after the Big Bang.
Thank you.
Don's got a hand up.
Go ahead, Doug.
Don.
Don.
Hi, yeah, it's just amazing the state of the art and how it's progressed over 50 years. I worked on Apollo 17 program, and there was an LSG experiment that was put on the moon by Apollo 17. It was a disaster. They didn't have the right moon compensating weights and it didn't work. But knowing the design of that experiment and what it was trying to detect, there was no way that instrument would have ever detected a gravitational wave. Just my experience.
Yeah, I mean, one of the important things that the Apollo missions did place on the surface of the moon were those corner reflectors, and then using, you know, laser ranging off those corner reflectors, measuring the distance very accurately of the Earth to the moon, has led to a lot of very strong constraints on alternative theories of gravity. So they did have some success with the corner reflectors, at least were successful. And there was actually a former professor here at Montana State University, Ken Nordvet, actually lobbied to get those corner reflectors put on the moon because he wanted to test, you know, Einstein's theory using them. And they said, well, that seems simple enough. All the astronauts have to do is get out, plonk down this corner reflector, and off it goes. So they're still working. A little bit dusty now, so not quite as clean as they used to be, but still being used.
Any other questions? See anybody, Jeff?
Can't see anybody online.
Okay. Thanks once again, Neil. Very much appreciated.
No problem. Well, thank you for having me. And yeah, I'll let you guys get to your business meeting, and I'll head out.
Well, actually, the first order of business, Neil, is that we would like to give you, as a small token of our appreciation, a club T-shirt or hat. I don't know if you can see my shirt or not. They look sort of like this, and Jeff here has got one of the hats. And there's two different styles of the hats. This kind of more traditional baseball, and there's one that's like floppier, doesn't have the structure to it. Would you be interested in well, if the hat, which type, and or you
Oh, yeah, wait, now I can see the hat a little better because I turned off my share screen. Okay, that, and you have a different hat. You said you have two hats. No, one hat.
and the shirts.
And the shirt. Yeah, I grab a hat. Always. I kind of collect hats. So
Okay.
thank you.
Do you think you'd like the floppier type or that type that you just saw?
I think just more a baseball cap would be good. Yeah.
And I think they come in like a small, medium, or a medium large.
Probably the medium to medium large.
Okay, if you can just send me your mailing address, we'll get that out to you.
Great. Awesome. Thank you.
Okay, 1 second here. Okay, thank you.
All right. Thank you.
Appreciate it. Okay. As far as our business meeting, I just had a couple of things. We continue to try to work on guest speakers. And I did actually secure one for February, and that is Ken Burton, who has actually spoken to us several times before, a variety of topics. This guy loves doing presentations. When you see him do it, you'll understand why he loves it, because he's pretty good at it. Anyway, he just happened to email me to give me a new phone number. And so, you know, I changed it in my records and thought a couple days left, well, wait a minute, it's a perfect chance to see if he'd return. It's been a little while. So anyway, we signed him up for February. Jack has managed to secure, Jim Shedlowski, who has also spoken to us several times, and he is going to be speaking to us in June. And Adrian, one of our own vice presidents, has got, I believe, 2 presentations that he says he's actually ready for right now. So I just got to get a hold of him and see which months he would like to do those. So we are making progress, but we still need to keep moving because the months keep clicking by. And you know, it's good to have stuff in the pipe, so because it's going fast. And the other thing to consider, as you notice, Adrian, he spoke to us a couple times last year, or I guess it was earlier this year. And some of our really, really good talks have actually come from our own club members. So if there's anything you'd like to talk about or know somebody that does, let us know. In fact, Neil actually was a lead that I got from Brian Close, who's out in Montana, who unfortunately emailed me and said he couldn't attend it via Zoom tonight, but he can see the recording. So always keep that in mind. You know, we're always looking for leads. So the other thing I had is I actually got a request for an observant event, believe it or not, for December 8th. Yeah, that's what I said. It gets more interesting than that. It's at one of the STEAM schools up on I think it's STEAM North Side here in Ann Arbor. But the person that emailed me said this event would start at 5:30, but he wants to have telescopes operating from 6 to 6:30. And then said it'd be kind of nice if he had somebody there to help people locate things in the sky. So I need a little clarification there, because really the way he worded it, you'd almost could take it that he wants us to bring telescopes and then let the people showing up use them to point at things. I don't think that's going to happen. But it's just a matter of maybe how you read it.
And for half an hour.
Yeah, and that's the other thing, you know, we're talking December of all things, it's cold. And I don't think too many people are interested in setting up telescopes for a half hour, you know, and just dismantle them. Nonetheless, Dimitri,
Did you say 6:30 or a 6?
6 to 6:30 is what he wants to do the
When is the
telescope.
sun setting in December? I don't remember, but it'd still be bright out, right? Or
No.
it would be.
Yeah, daylight savings time still,
Yeah, it'll be getting
like
dark.
5:30, 6, it gets dark.
Yeah, so it'll be getting dark. But,
Yeah.
again, it just doesn't seem worth it. Nonetheless, I'll send something off the club and see if anybody's interested. Somebody did say was it you, Jeff? Somebody did.
No, I would set a telescope up.
That was you, Don. Yes.
Yeah.
thank you.
I would do it.
So,
And I got
That's the day after full moon.
is it really?
Oh,
I didn't even look at that yet.
Yeah, you said the 8th. You said the 8th, right?
I did.
so lunar view.
And the interesting thing is the day before is when something interesting happens.
Yeah, we
What's
got
that?
The occultation of Mars.
Oh,
The lunar occultation of Mars happens, I don't know, when does it? It varies quite a bit depending on where you live, but it's a little after 10 o'clock, I think, for us.
yeah. So I don't think they'd want to be out that late anyways, my guess, but
Plus, it's unless you have a telescope per person, it's
it's a Thursday.
useless.
Yeah, the only real thing I can see that's interesting is the moon and Mars are next to each other, and I'm seeing if Orion's up. It is, but it's next to the moon, so it would be a terrible,
Yeah,
terrible day for observing.
yeah. And let's face it, in all likelihood, the weather is going to tear us up anyway, so. Unless we don't plan on it, then the weather will be okay. So let's not plan on it, then we can all go observing on that day because we know it'll be clear, right? Anyway, I'll send an email, see what kind of interest we can get in that. It sounds like Don's interested. I guess I am somewhat, the only thing I'm concerned about is it starts at 5:30 and it's a work day. Typically, if I schedule something like that, that's the day that everything happens late in the afternoon and messes me up, so. But we'll see. Anyway, That's all I had, so I would like to go to officers and we'll start with Jeff.
We had our usual 30-60 split for members. I think total was 27. 18 max on Zoom and 9 in person.
And just trying to see who else is out there. Is that it, Jeff?
Yeah.
Okay,
think
thank you
so.
much. I see Jim. You're muted, Jim.
Can you hear me now?
Now we
Yes,
can.
we can.
Okay. The only thing I have is our open house schedule for next year. I sent that out a couple of months ago, the proposal. Since we haven't talked about it at all, I doubt anybody's ready to talk about it tonight, and since our December meeting is not going to be online, I would imagine we could try and finalize it in January.
Sounds reasonable.
Yeah.
You know, I realize that Fred doesn't want to broadcast the music he's using, but you know, those of us who aren't ready to be indoors in public places, you know, I guess, you know, that meeting is going to be pretty sparsely attended. And that's all I've got.
Thank you, Jim. Dave.
Yes, so last night, there was a private open house at the Detroit Observatory. He had an opportunity to talk with Gary Krantz, who's the director, and also Austin Edmister, who, as you recall, talked to the club in August. I mean, nothing definitive, but I mean, certainly one idea that's been out there is the club used to meet at the Detroit Observatory, and they would be certainly happy if we started meeting there, you know, instead of Angel Hall. There might be some advantages to that.
Yeah, one thing's getting in the building.
Yeah, well, Austin said he'd be there. So,
Hey, there you go.
so it wouldn't be a question of you not having the right code and not being able to get into the room. So the other thing, there was, they had this poster and it was, and they had like, I think it was like M15, Eagle Nebula, Jupiter, Saturn. So these are all images that have been taken through the FIT over the past year. And as I assume some of you might appreciate, they've gone through a little learning curve in terms of how you convert the raw images into images that could be displayed. And you know, I told him, look, the members of the club have been doing this sort of thing, and he'd certainly be agreeable if some people wanted to compare notes. And I mean, I imagine they probably could learn more from us than the other way around. So I'm just putting that out there if there's any interest in that. So I did get a memento, a Detroit Observatory name tag, which I'm not sure what I'll do with it. But, there were some other things I'm still working on, but I don't have anything tangible at this point. So that's it.
Thank you, Dave. I appreciate you doing the minutes too, especially 2 months in a row.
Thank you.
Hopefully get another vice president to do it next month, so. I do not see Adrian out there. I don't see Brian Odom, but I did notice, I think I see Brian Close, and I believe you actually gave us the lead to Neil Cornish. And I didn't think you were gonna make it tonight, but I believe you did. So I think that's very, very cool that you got to see them. And thank you, Brian. Jack.
As for the observatory, just getting it ready for winter. And the other thing is later on, I'll contact Dave about storing the 17.5 inch in his garage again, his work shed. See if he still, if we can still do that or not. Other than that, that's all I have to say about the observatory for right now.
Yeah, let me know, Jack, when you want to do that. I can help you move it.
Okay, that's fine. I've just been busy the last month or two here, and I'm just getting over a lot of other things I was doing. And so, yeah, I'd like to try and get that done sometime between now and December or something, before Christmas, before the club meeting, stuff like that. I just don't know exact date right now.
Yeah, well, the batteries aren't going to do very well if we don't get them in a warmer space soon.
That's an issue that we need to test and look at again, like we did the last time. The individual batteries underneath the mirror cell, things like that. I just wonder if they're really still that good. They're really putting out the right amount of power that they're supposed to.
Yeah, I haven't used the scope for a while. There's someone who used it this summer on the meeting? And how did it work? Because it's been over a year since I've used it.
We had it at Astronomy at the beach.
Okay.
They had problems with it tracking it. And I ordered some new equipment, a new wire for it, handheld coordinate. I think I sent out some pictures showing the one had split. You can see the wires coming through the cord.
All right.
Pause that, but I put that on it. I did test it, and I got it to move and go in declination, yeah, azimuth and altitude. And doing testing like that, got it to respond to the, but we really need to take it out at night, set it up again, and test it with the Sky Commander, because we did some other things with it too. The side that has the steel rod for the altitude and azimuth, it was always flopping around back and forth, and I got some spacers and that to put inside there so that bar is straight now and it does not move back and forth. And that bar moves back and forth, it changes and it rotates that encoder, and that's where that'll give you those weird readings. 1 minute you're looking, next minute somewhere else. So I'm hoping doing all those little things have helped to solve the problem. And I did get the new it's used to control the crosshairs on the finder scope, the light with the battery. I forgot that there's a technical name they call the thing, but we ordered a new one from High Point Scientific. They had one that would fit the threading and everything. It just threaded right in.
Oh, the illuminator?
Yeah, it's they call it illuminator deck something or whatever.
Yeah.
It's the reticle illuminator.
Yeah.
Pardon?
It's the light that illuminates the reticle on the finder scope.
Yeah, that's what it is. So we got that in, and I got
Some work needs to be done in the telescope to remount the Telrad finder. It's mounted to the black plastic, and it's just not usable that way. A board needs to be put from the top ring to the bottom ring, and the Telrad attached to that, and that could be a winter project.
yes, and it's a very good point, because we talked about that, and I had some wood left from the finish wood that we did the telescope in. And I did cut off a piece, and I've got 2 coats of varathane on it and everything. So yeah, we get together, we can assemble and put that on and test the whole thing out. And get it fixed up. So that's another thing we can do too. Other than that, that's really all I have to discuss about the observatory and the 17.5 inch. It's just now that time frame of the year is when we have to do some maintenance and work on it. That's all. With that, I'll turn it back over to our Mr. President.
Okay, thank you, Jack. And I don't think I missed any officers. Doug Scoble sent me an email actually while we were meeting here and said he wasn't going to make it, but he will send a report tomorrow. So we have that for the minutes. And Amy emailed me, it was either yesterday or earlier today, and said that she's not going to make it, but she wanted to file a report, which is she has no report. So that was brief. With that, does anybody have anything else?
Yeah, Charlie,
Yes.
this is John Wallbank, president, the current president of GLAC, Great Lakes Association of Astronomy Clubs. We are going to be resetting our board of directors, our officers, and our planning committee at the January meeting, which will be, if things hold out here, which will be January the 19th, the third Thursday, January. It's going to be on Zoom. And we're always looking for people who want to participate in the planning committee, or even better, people who want to take up an officer's position. There are the only officer's position that is really set at this time is the treasurer. Adrian Bradley is going to continue as treasurer. We have some people that would actually would like to kind of get some help and reduce their responsibilities. Now, one of the things about GLAC is that if you become an officer or participate in the planning committee, especially if you're become an officer, it's the obligation of the current officer in that position to assist you throughout your first year in that position. So there's kind of a mentorship there. And I think, you know, every one of the officers right now, Jeff is the secretary, I'm the president, Tim Campbell of the Ford Club is the vice president, and Brian is our communications director. There are a number of opportunities there. And of course, being on the planning committee, we always welcome help with the planning committee, because it seems everyone on the planning committee has something to contribute and helps to dissipate the burden of all the rest of us, and also helps to expand the event. So that's going to be in January, the third Thursday, the 19th. Please think about participating. You'd all be welcome. And our meetings will continue to be on the third Thursday of the month. The event is going to be the 22nd, 23rd of September in 2023. And I have to say that it's a lot of work, but it's also very rewarding and a lot of fun. Really good group of people. So please think about joining up with us. Thank you.
Hey, John, one correction. Our meetings are on the second Thursday and it's January 12th.
Yeah, I'm sorry. I got that confused with another outfit that I'm in. So yeah, the 12th.
Okay.
Yes. Okay. Well, that's
January 12th.
I need help. I need a replacement. I need help. I'm aging out here.
Well, you asked and then you just demonstrated it, right? So
That's
it's a good sales tactic.
yes.
Say
Thank
what ATB is again?
Astronomy at the Beach is September 22nd and 23rd of
22nd,
2023.
23rd, okay. Thought I had those dates. I just wanted to make
Friday,
sure.
Saturday.
And I
at Island Lake
believe
State Park.
that does not conflict with our monthly meeting next.
It should not.
Yeah, so that's cool. Anybody have anything else? Thank you, John. Okay, hearing nothing, would somebody like to make a motion to adjourn?
Motion to adjourn.
Support? I have support. Anybody opposed? Okay, thank you very much, everybody. We'll see you next month.
Good night, people of Earth.
Take care.
Good night, everyone.
Good night.
Ooh.
Okay, Earthlings.